Hello. In this video, I show you our simulation for the Apollo 11 mission that launched on July 16, 1969. This is the mission where humans first landed on the moon. Before we start, we assume that you've already viewed our other video, Lunar Orbiter Mission Design. Now, open the example orbit project file, Apollo 11. NASA chose the date for the launch, so the parking orbit inclination would be approximately equal to the Moon's orbit inclination relative to Earth. We got much of our information about this historic mission from public documents, but we were not able to determine the exact location and time where the parking orbit insertion actually occurred. Therefore, we used our best guess. As you can see, we assumed the parking orbit insertion occurred several hundred kilometers east of Cape Canaveral, Florida, at 1:44 p.m. Coordinated Universal Time. We used an orbit inclination equal to 29 degrees and 48 minutes. At 4:24 and 10 seconds p.m. UTC, the Hohmann transfer orbit was initiated to enter a translunar trajectory that intersects with the Moon. This occurred on the opposite side of Earth relative to where the spacecraft would approach the Moon. The delta V, or change in velocity, required was 3,147 meters per second, which required a significant amount of fuel. On July 20th, at approximately 5:20 a.m. UTC, the spacecraft passed in front of the Moon. If the lunar orbit injection burn was aborted, the spacecraft would slingshot off the Moon and return to the Earth. Later, you will delete this 20-second deceleration and watch the spacecraft return. At 6:41 and 30 seconds a.m. UTC, the lunar orbit injection burn occurred in the opposite direction of velocity and behind the Moon. We use 42.5 meters per second squared of deceleration for 20 seconds. This is slightly more than 4 times the acceleration due to gravity and can be tolerated by the human body for short periods. The spacecraft then slowed to enter a low-altitude lunar orbit. Finally, I want to demonstrate what happens when the last rocket burn is deleted. Do that now and then recalculate the orbit. Note that the spacecraft returns to Earth. This was designed into the mission for safety purposes. We have not yet modeled the lunar landing that occurred later. We encourage you to do this yourself. Here are some of the things we learned from the simulation. 1. To get the widest launch window for a lunar mission, the parking orbit inclination must be equal to, or close to, the Moon's orbit inclination. That's difficult to get without using lots of fuel to do a parking orbit inclination change. 2. The date selected for that mission was July 16th, 1969, and it corresponded with a desired lunar orbit inclination that could be duplicated with a Cape Canaveral launch without additional fuel. 3. The fact that the two orbit inclinations were almost the same made getting to the Moon easy. However, the location of the parking orbit insertion position and inclination made drastic changes in the lunar arrival times. 4. The spacecraft passed ahead of the Moon. This was to ensure that, if the lunar orbit injection rocket failed, the spacecraft would use lunar gravity assist to return to Earth. 5. The lunar orbit injection burn occurred behind the Moon and was opposite the velocity. In other words, it was used to slow the spacecraft so it would enter a lunar orbit. 6. NASA had to include solar gravity in their calculations. We know this because we turned off solar gravity and found that the spacecraft crashed into the Moon, assuming the same lunar orbit injection burn. A different burn is needed to save the mission when the Sun's gravity is considered. Thank you for watching this video. If you find it useful, please give it a like and consider subscribing to the channel. We will be producing new content in the future, so if you want to be notified when new content is added, click on the notification bell. We need your feedback, so leave comments on our webpage. Goodbye.